Jupiter's magnetic field is not only the most powerful in the solar system, but it also has unique characteristics that make it a subject of ongoing research and discovery. The origins of this mighty field lie deep within the planet's structure, where a conductor of metallic hydrogen generates the electric currents that power Jupiter's magnetism. Unlike Earth's magnetic field, which is primarily generated by the motion of molten iron in its core, Jupiter's magnetic field is created by the behavior of hydrogen under extreme pressure. Within the planet's innermost regions, hydrogen is compressed to such an extent that it takes on metallic properties, allowing it to conduct electricity. This metallic hydrogen, in combination with Jupiter's rapid rotation, Jupiter rotates once every 9 hours and 55 minutes, sets the stage for the creation of a massive and extremely powerful magnetic field. The strength of Jupiter's magnetic field is truly staggering, with the magnetic field near the planet's surface being 14 times stronger than Earth's. As the magnetic field extends outward, it grows in size and complexity. It doesn't just emanate from the planet in a simple, uniform way. Instead, it is twisted and stretched into unique shapes by Jupiter's rotational speed and the influence of the planet's intense atmospheric conditions. This twisting of the magnetic field leads to a phenomenon known as the magnetic tail, an extension of the magnetosphere that stretches millions of kilometers away from Jupiter, almost like a cosmic comet's tail. Jupiter's magnetosphere is not just a shield for the planet, but also for its moons and the surrounding space environment. It acts as an impenetrable barrier against solar wind and cosmic radiation, both of which can be incredibly damaging to planetary atmospheres and life as we know it. The magnetosphere prevents much of this high-energy radiation from reaching Jupiter's surface, making it one of the few places in the solar system to have such an intense, protective magnetic field. The extent of the magnetosphere is mind-boggling. It can stretch out as far as 12 million kilometers from the planet's surface, which is 7 times the size of Earth's distance from the Moon. Within this enormous shield, the charged particles are trapped in the magnetic field, where they circle around the poles, creating intense radiation belts. The magnetosphere doesn't just protect Jupiter. It is a dynamic system that interacts with space weather, such as the solar wind, in complex and fascinating ways. This interaction between Jupiter's magnetic field and the solar wind creates plasma waves, some of which are so powerful that they emit radio waves detectable from Earth. The magnetosphere also acts as a dynamic space weather system, influencing the charged particles within it to move and shift. In a way, Jupiter's magnetosphere plays a role similar to that of a cosmic weather system, affecting the solar wind, magnetic fields of neighboring planets, and even helping to regulate the solar system's radiation environment. Jupiter's powerful magnetic field does not only affect the planet itself, it also has significant impacts on its many moons. Jupiter's magnetosphere is like a vast magnetic ocean, and some of the moons, particularly Io, Europa, Ganymede, and Callisto, swim through this ocean, experiencing its magnetic influences in dramatic ways. Io is the most volcanically active body in the solar system, and its volcanic eruptions are intricately tied to Jupiter's magnetic field. As the Moon moves through Jupiter's magnetic field, it interacts with the charged particles in the magnetosphere. These interactions generate electric currents, which in turn power the volcanic activity on Io's surface. These currents create a twin effect of magnetic forces, amplifying the planet's field and creating an electromagnetic atmosphere around Io. This results in the Moon emitting a faint but detectable plasma torus, which is a ring of electrically charged gas that orbits Jupiter along with Io. Europa, one of the most intriguing moons of Jupiter, is known for its ice-covered surface and the possibility of a subsurface ocean beneath. The Moon exists within the protective boundaries of Jupiter's magnetosphere, but it is still exposed to intense radiation. The magnetic field interacts with Europa's surface, and the interaction creates electrical currents in the ice. These currents may even contribute to the chemical reactions that could be essential for life beneath the ice shell. Europa's thin atmosphere is constantly bombarded by radiation from Jupiter's magnetosphere, but the planet's field keeps the majority of harmful solar radiation at bay. Ganymede, the largest moon of Jupiter, has its own magnetic field. This is the only moon in the solar system known to have an intrinsic magnetic field. Scientists believe that Ganymede's magnetic field is generated by a liquid iron-nickel core similar to Earth's. The interaction between Ganymede's magnetic field and Jupiter's much larger one creates a complex system of magnetic interactions, including auroras around the moon's poles. These interactions give us a unique opportunity to study the magnetic dynamics of a moon with its own field embedded within the far-reaching influence of a massive planet's magnetosphere. Callisto, the outermost of Jupiter's Galilean moons, is less affected by Jupiter's magnetosphere than its inner counterparts, but it is still within the larger influence of the magnetosphere's radiation belts. The moon has a thin atmosphere made mostly of carbon dioxide, and although the radiation is not as intense here, the magnetosphere still plays a role in shaping the space weather around Callisto. While Jupiter's magnetosphere is an incredible shield, it also creates intense radiation belts that can be both a blessing and a curse for space exploration. These belts are made up of high-energy particles that are trapped in the magnetic field, and they create one of the most hazardous environments for spacecraft in the solar system. The radiation is many times more intense than anything we experience in Earth's radiation belts, and any spacecraft venturing into this region needs to be equipped with special shielding. For example, NASA's Juno mission, which arrived at Jupiter in 2016, was designed to withstand the radiation environment within Jupiter's magnetosphere. The spacecraft's instruments are housed in a specially designed radiation vault, and it carries protective materials to minimize the damage from the charged particles. The science from Juno and other missions like Galileo, which studied Jupiter from 1995 to 2003, helps scientists understand not only Jupiter's magnetic field, but also the radiation environment that future missions to the Jovian system will face. Jupiter's magnetic field plays a pivotal role in the solar system, especially in its interactions with the Sun's solar wind. As the largest planet, Jupiter acts as a cosmic sentinel, its magnetosphere deflecting much of the solar wind and helping to shield the inner planets, including Earth, from high-energy radiation. In a way, Jupiter serves as a giant magnetic filter in the solar system. By deflecting solar winds and cosmic radiation, it helps maintain a more stable radiation environment for the planets closer to the Sun. While it is unlikely that Earth would be entirely unprotected from radiation without Jupiter's magnetic field, Jupiter's presence certainly contributes to the overall stability of the solar system's radiation dynamics. Scientists hypothesize that without Jupiter, the solar system might have faced more intense solar wind activity, which could have had consequences for the development of life on Earth. Jupiter's magnetic field, by acting as a protective force, has likely played a role in safeguarding Earth's atmosphere and shielding it from cosmic radiation for billions of years. Jupiter's magnetic field continues to be a focus of scientific exploration, especially as humanity plans future missions to study its moons and its atmosphere. With missions like Europa Clipper and the upcoming JUICE, Jupiter Icy Moons Explorer, mission by the European Space Agency, the study of Jupiter's magnetosphere will continue to be a central part of our understanding of planetary systems, magnetic fields, and the broader cosmic environment. Future space exploration of Jupiter's moons and beyond will require a deeper understanding of how Jupiter's magnetic field shapes the local space weather. This knowledge will help us not only in mission planning, but also in protecting spacecraft and designing safe and effective exploration strategies. Jupiter's magnetic field is a remarkable and powerful force, and its study will reveal much about the dynamics of giant planetary systems and the unique environments of the outer solar system. Jupiter's magnetic field is a cosmic marvel, a shield of protection, a driver of scientific discovery, and a testament to the wonders that exist in our solar system. The planet's immense power, both in terms of its gravitational might and its magnetic influence, continues to provide new avenues of exploration and deepen our understanding of the universe.